Hey everyone, it's STEM time with Navya and Aishwarya. We are your hosts, Navya.
And Aishwarya. So, following the theme of last week, for today's episode, we are going to be doing an extension to our episode about amazing abstractions. We really enjoy talking about abstractions, and we wanted to go a little deeper into the topic so that we can help you guys master the topic and understand computer science. But before we dive in, like promised, Navia is going to give you guys a quick update on the current event for today's episode.
So, the current event for today's episode is that on May 22nd, a research team at the Monash University recorded the world's fastest internet speed from a single optical chip of 44.2 terabits per second.
Awesome. So let's talk about our agenda for today. The questions we are going to be addressing include uh, what are examples of abstraction in the real world?
Then we're going to talk about what are the advantages of data abstraction.
What are the abstractions found in elements of programming?
What makes a function good, and what are some different types of functions?
And finally, we're going to be talking about the difference between abstraction and encapsulation.
So, the first question, what are examples of abstraction in the real world? So, this is really fascinating because sometimes we're using abstraction without even realizing it. A lot of the time, we assume that some processes are actually more simpler than they are, and we take that for granted. Abstraction not only shows the important and essential things to the user and hides complex processes.
So, a really good example of abstraction would be a bike or an ATM because they're really, really simple machines and they only require either one constant movement or a click of a few buttons. But sometimes we just don't realize that there are more complex processes involved and happening. But since we're able to use simple interfaces and we only interact with simple interfaces, we don't actually understand what's going on inside and the complex processes happening all the time. So, we're going to talk about the advantages of data abstracting. Before we dive in and talk about the advantages, though, I just wanted to remind you guys to check out SiteBay for more information and applications of abstraction in Java. So, the advantages of data abstracting are very important because we need to understand its significance. So, something we've already mentioned in our previous episode was we talked about the reusability and the use of abstraction and how it increases the reusability and how it helps avoid repetition.
Another thing that is really nice with abstraction is that it increases the readability of the code because it eliminates the complexity. So something we are new to here is the enhanced security, and since data abstraction implements classes and objects, it's cool to see that access can be denied to other classes of accessing the member functions of the base class and the data members. In simple terms, it helps increase security of an application or program by only revealing important details to the user.
So, one of the most important advantages and best features of abstraction is that without affecting the user at all, abstraction can independently change internal implementation of class.
So the next question we're going to address is, where are abstractions found in the elements of programming? So composingprograms.com was extremely helpful in explaining this.
I remember how they talked about programming language is more than just a way to instruct a computer to perform tasks. And a language is also a framework within which we can organize our ideas um, because of the processes that we have to execute. So, a small tip for everyone who's planning to go into programming or who already is a programmer, it's important to remember that while it is only the machines that are executing the code, They actually have to be written in a very organized manner so that other programmers and other code readers in the community are able to read it easily.
So additionally, I just wanted to add that this makes it significantly easier to communicate these programs and ideas, not only for you to read it easier and see it in an organized manner, but for others to read and be able to comment and see exactly what you are doing without being extremely confused.
Right, and I think it's also important that when we talk about a specific language, we have to pay focused attention to the means that the language provides for combining simple ideas to form a more complex idea. And every powerful language has three mechanisms.
So these three mechanisms are: the first one is expressions and statements, which are essentially representative of the simplest building blocks that the language provides. Then the second one is means of combination, through which you can compound elements which are built from simpler ones. And the third one, which is means of abstraction, which you can use, compound elements that can be named and manipulated as units. And elements of programming include numbers and arithmetic operations, which are primitive built-in data values and functions, nested function application, which provides a means of combining operations, and binding names to values provides a limited means of abstraction.
Great. So let's move on to our next question. What makes a function good? So, fundamentally, the qualities of good functions all reinforce the ideas that functions are abstractions. But to actually understand what makes a function good, we have to understand the qualities behind it, not just a collective general assumption. So, let's talk about the qualities of a function and what make a function good. Each function has to have exactly one job. The job that the function has should be identifiable with a short name and characterizable in a single line of text. Functions that perform multiple jobs in a sequence should be divided into multiple functions to simplify the process.
So another a good quality is to never repeat yourself. And multiple fragments of code should not be redundant. And so what I mean by this is that logic should only be implemented once, given a name, and applied in many different situations. So if you find yourself copying and pasting a block of code, you probably have found a perfect opportunity for a functional abstraction. So just call the function. It's a lot easier to do. Also, functions should be defined generally. Squaring is not in the Python library precisely because it is a special case of the power function, which raises numbers to the arbitrary powers. So adding on to the previous question about why abstractions are necessary, we have seen that functions are a method of abstraction that describe compound operations independent of the particular values of their arguments. That is, in a square, if we are making a function, we can write definition or def square of x. That would be the name of our function. And inside the function, we would say return x times x. So every time you need to square a number, you can just call this function.
So we're not actually talking about this when we're not actually talking about the square of a particular number. We're trying to talk about a method to obtain the square of any number. So we could do multiple things to never actually explicitly mention the square uh, by writing expressions like 3 times 3 is 9. 3 squared is also 9. But since you've written 3 times 3 is 9, you have not actually mentioned the square function. There's also another type. If you do 5 times 5, for example, you'd get 25.
But actually, this practice would be enough for simple computations such as square, right? We could always just say do 3 times 3, and it's not that difficult, right? But this would be extremely difficult for more complicated examples such as absolute value or finding the Fibonacci sequence numbers. So, to express certain general patterns as named concepts, we will need to construct functions that can accept other functions as arguments or return functions as values. Functions that manipulate functions are called higher order functions. So a function is called recursive if the body of the function calls the function itself, either directly or indirectly. That is, the process of executing the body of a recursive function may in turn require applying that function again. Recursive functions don't use any special syntax in Python, but they do require some effort to understand and create.
So let's move on to our last question for today's episode. What is the difference between abstraction and encapsulation? So, in our previous episode, we talked about how abstraction is a simplified version of something that is more complicated. And we gave you guys some examples in the previous episode and today's episode. But when we talk about encapsulation, it describes the idea of putting data in bundles and using processes on the data within a unit.
So, in other words, while encapsulation means that the information is hiding and it's hiding specific information through control access, abstraction means to only show necessary details.
And the major difference between encapsulation and abstraction is that encapsulation is not providing you with full security, whereas abstraction has enhanced security, which leads to abstraction being more beneficial and having more advantage points when being compared to encapsulation. And while both of them do have their differences, encapsulation and abstraction are both used widely throughout the programming community, and they're both very, very important in object-oriented programming.
Yeah, and so that's it for today about amazing abstractions for this episode about amazing abstractions part 2. And I hope you guys had a fun time listening to this podcast. And don't forget to tune in to our upcoming podcasts. Feel free to reach out through our Instagram page, STEM Time Podcast. Please follow our Facebook, Twitter, Instagram, and YouTube accounts. Don't forget to keep learning new things. See you in the next episode. Bye-bye.
Bye, guys!